Hi, welcome to the chapter for data path. This is the second part, and we will discuss in this lecture different data paths, and we'll start with adders. Of course, in the last, let's talk about what we have covered so far about adders. What we did, we looked at one bit adding one bit like 1 plus 1 plus 1, and we said we could do this with full adder. Of course, if you are adding two numbers, that's a half adder. um, then we looked at adding two multi-bit numbers like so, and we have seen how we can construct those. And now in this lecture, we will look at how we can add multiple in-bit numbers like so, and how we can add those. Okay, so this is the first topic in this lecture. So let's go back to the slides, and you see here that we're gonna look at this multi-input adders. So for instance, here we are adding 0001, which is equivalent to 1, and 01117, number 7, and 1001, which is 13, and 0010, which is 2. So we're adding 1 plus 7 plus 13 plus 2. Now, if we want to add this the conventional way, or the easy way, I should say, we can use carry propagate adders to add the very first two numbers, and we get, see, we are adding 1 plus 7, and this is 8. Okay, and then the result of these two, we add them to the third number. Okay, so 7 plus I'm sorry, 8 plus 13, that is 21. Okay, so we get the results by adding the 8, the result of the first two, with 13, which is the third number, and we get a sum here, and then we add the sum with the fourth number, okay, which is a result with this one, which is 23. All right. um, so this method requires one, two, three carry propagate adders. So if I have k numbers, k in-bit numbers, we will have to go through k minus 1 carry propagate adders. Unfortunately, despite the fact that this is easy method, but unfortunately it is slow, very slow. Why it is slow? These carry propagate adders are slow, and we have seen in the last chapter how we have invested significantly with different methods like look ahead adder and tree adders, just to try to minimize the delay of these adders. So we would like to look for other methods. Okay, so let's see what we can do as other methods. One of the methods is that we will compress the number of rows, and we will compress the number of rows by a method called or by a column compressor called carry save adders. And let's go to the whiteboard here just quickly and explore what this method is, and see what's the idea behind this method. Basically, what we are trying to see here, if you have a multi-bit numbers, I'm representing a number here with a line. So obviously, what we try to do in the first method is to add those with adder, you get a number, and add those with an adder, and you get a number. Okay, and let's just say, for example, you have another. So you add those with another adder, okay, and you get a number, and then what you do, you add these with another adder, okay, you get a number, okay, and then you add those with an adder, and you get a number here. So this is what we have done so far. So we serially add those numbers, or in parallel. Okay, what we did, the method that we explored, we have done it serially. This is parallel. Okay, so let's see the method that we have explored earlier. What we did, we say add first two numbers, then add the third number, then add the fourth number, then add the sixth number, and so on and so forth. You can do those in parallel, okay, in a binary tree kind of fashion. So we said that this is slow, and also this is slow. Okay. Okay. So what can we do? Well, it's time to think of a new strategy or new methods. And one way to do it is really what we do. We try to reduce the number of rows that we are adding. And how is that? So basically what we do, we take three rows and we compress them into two rows, and we continue doing so. Let's say, for example, you do this, and so suppose I have nine numbers to add. I compress those three rows or three numbers into two numbers, and three rows or three numbers into into two rows or two numbers, and three rows into two, and then I take these three and compress them into two numbers or three rows, and compress them into, and then I take these two and compress them into two, and then I take these three, all right, and compress them into two, and now I can use at the end the very slow carry propagate adder or any of the adders. These compression schemes, they are fast. Okay, that's the critical thing. They are fast, so I can do them very quickly. So how can I compress three rows or three numbers into two rows or two numbers? Okay, so this is what we'll do. We'll try to explain what we are trying to do here with an example. Suppose I'm adding these two numbers, these three numbers. Okay, so this is three numbers, or what referred as rows. We need to compress them to two numbers. So what we do is that we will generate a sum number and a carry number. Okay, so let's see. Add now 1 plus 0 plus 0. That's a sum of a 1 and a carry of a 0. Notice there is no carry propagation here. Okay, 0 plus 1, that's a sum of a 0 and a carry of a 1. 0 plus 0 plus 1, that is a sum of a 1 and a carry of a 0. 1 plus 0, that is a sum of a 1 and a carry of a 0. Now, I can say that I have compressed this into this. So if I can call this number x, y, z, right? I can say that x plus y plus z equal to sum, watch, 2 multiplied by the carry. Okay, let's double check our math here. What is the value of x here? It is 9. Plus, what's the value of y? 2. What's the value of z here? 6. Okay, all right. So that comes into 17. Okay, all right. Now, what's the value of the sum here? The value of the sum here, it is 13, right? 13 plus 2 times, what's the value of the carry? 2. So 13 plus 4 equals 17. Aha, they are equal. They are equal. So what did I achieve here? What I achieved is that I compressed. I like to use the word compressed. I compressed three numbers into two numbers. These three numbers has been compressed into two numbers. Now we have to be careful of how to write this. We say that these two numbers are 1 0 1 1, which is this number, and this one we say 0 for the carry. Why the carry? Because we multiply it by 2. 0, and then I write this number 0 1 0 0. Okay, that means that as I compress the numbers, the width of the numbers increase, which is very important, because somewhere that meaning of the numbers has to go somewhere. Okay, so we increase the width of these numbers. Okay, but the critical thing that I'm using, the most important thing that I'm using, is that I am reducing the number of rows that I need to do, or the number of numbers that I need to add. And as I reduce the numbers, I will make my adder faster. Watch as I add here. All what I need is what? A full adder, because I'm adding 3 bits and I'm producing some carry. Here, same. Here, same. Here, same. Okay, so, and that is very quick. Very quick, one step, and I'm generating the sum row and the carry row. Okay. All right, so with that explanation, let's go back to our slides and see what we have here. So basically, as we said, we have x plus y plus z. These are the numbers. We produce a sum plus 2 times the carry. And we know that these generated by a full adder. And we call this full adder, in this context of compressing, we call it a carry save adder. A carry save adder. We'll see how we will use this in a second, how we can produce a better sum. So let's take a look at the example. These are our 4 numbers that we were adding. So this is our 4 numbers that we are trying to add. So what we will do, we will add the very first 3, okay, and produce a sum and a carry. So watch, this is the first number, this is the second number, this is the third number. Okay, so this is the sum row, and this is the carry row. Watch here, he is shifting this to the left, indication of multiplication of 2. And actually, if I were the author, I would add it just a 0 here to indicate that it is multiplied by 2. So I'm adding these numbers, I'm generating a sum and a carry. So you can see this is the sum row, and this is the carry row. Now I add the sum and the carry, plus the fourth number, which, as you can see here, that's what he is doing here. He is adding the carry and the sum line, and plus the fourth number, which is right here, okay. Then he is producing a sum and a carry. Now once you are down to 2 numbers, then you use the carry save adder, the carry propagate adder, our regular adder. So now you have just some 2 rows, you add them like we used to. So now you can see this is the final carry and the final sum. You add them like you are adding any 2 numbers, and you use a carry propagate adder. And now notice this carry propagate adder, which is slow. I'm using just one, okay. And the previous ones are what? Carry save adders. These are fast, okay. All right, so these are fast carry save adders. Okay, so for k numbers, I need k minus 2 stages of carry save adders, and I need final CPA. This method is much faster than the serial method that I used in the earlier slides. Okay, so you can check that. Once you get this number, you can see it is 23, which was produced in the early method, as we saw. Okay, all right. And again, why this is fast? Because it is a full adder delay. That's it. No carry propagation. Okay, so now here we look at the schematic of how he is tying these. So these are the first 3 inputs. All right, the first 3 inputs. Obviously, he is stitching the bits. Okay, so bit position number 1. They go to the first adder, and we can see that produces a sum and a carry. Notice why this carry going to the next stage, because it is the carry is shifted one bit to the left because it's multiplied by 2. So this bit here produces a sum. This is a sum, this is a sum, this is a sum, and the sum goes and goes to the very next bit, but the carry goes to the next stage. Somebody might say, well, this is propagation of the carry. I said, no, 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 because you see, you are having just a delay of one full adder. So this is the addition of the very first three numbers. And now in this step, what do? I add the sum, okay, the sum and the carry from the previous stage and the fourth number, which is the D's, okay, and I produce a sum and a carry, 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 and then I use a carry propagate adder to add the last two rows of sum and carry, okay. So this method requires k minus 1 of carry save adders and 1 carry propagate adder, and k minus 2 of CSA and 1 carry propagate adder. This is much faster than k minus 1 of carry propagate adder, the serial method that we saw previously. Okay, so now we have discussed adding multi-bit numbers. um, we will shift gears and change topics. One of the data paths, important data paths, is circuits that are able to detect ones and zeros. Why ones and zeros? Why should we bother about detecting ones and zeros? Well, for example, you need to detect if you have an ALU, and the result is 0, typically you would like to detect if the result is 0, okay, and that's generates something like called the zero flag, for instance. And in counters, when you count the counters, typically when the counter reaches 1111, this is when the counter saturates, and you would like to detect this condition so that you can you know that you saturated the counter saturated to the maximum value. So there is a need for detecting the case of a 0 or the case of 11111111. So because these circuits are common, or we would like to include them in the data path and see how we can design them. Now, one of the circuits here that is used for zero detect is or one detect is this multi-stage. Okay, you see here. Of course, he's using NAND gates here, NAND followed by NORs. These are, by the way, NOR. These are NORs. Okay, these are NORs. This is a NOR gate. Okay, don't be fooled with the direction of the bubbles, but these are NOR gates. NAND followed by NOR gates. So this is basically a 4-input AND gate. Now, this is a 4-input, but implemented in 2 stages. So 4-input and then followed by this NAND gate. So this is how you implement, for example, a detection of a 1 on 8 bits. On 8 bits. Now, let me just go to the whiteboard and include interesting discussion here. Is that okay? Suppose, for example, in these circuits, we would like always to, whoops, suppose I want to detect a 1 from 16 inputs. Let's say I have x0, x1, x2, x3, x4, x5, x6, x7, x8, x9, x10, x11, x12, x13, x14, and x15. So we would like to detect, implement a one detect for this circuit. So what do? We do a NAND gate here, 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 a NAND gate here. Now followed by a NOR gate, a NOR gate, a NOR gate, a NOR gate, followed by a NAND gate, followed by a NAND gate. Oops, sorry. And followed by a NOR gate. Okay, so this is one implementation. Now another implementation we do is that we can notice that here the grouping here is based on two input gates. I could do another implementation. 1 2 3 4, 1 2 3 4, 1 2 3 4. I'm grouping by fours here, and 1 2 3 4, and then a 4 input NOR gate. Okay, so notice what I have done here. Of course, if you push back the bubbles here, you will find that you have implemented a 16 input NAND gate. Okay, so question: why can't I just do a 16 input NAND gate one shot? Well, this is very complex and very slow, and you don't want to do that. Okay, so that's why we have to go through, we implement through stages. Okay, so the second question: which is faster, this one or this one? Well, in fact, you really need to simulate, because what you have here, this tree has 1 2 3 4 stages of small gates. So 4 stages of small gates, and typically they are fast, right? And here, well, you have 2 stages of more complex gates. All right. So who wins? You have to simulate. We don't know. You go to spice simulation and simulate them. I would say probably, I would guess probably with good optimization, these may win. Okay, the 2 stages, but again, it really depends. So you have to go to spice simulation and simulate them. All right. So now let's go back to the slides here, and oops. Okay, so we see here that this is the one detect. All right. Notice this is actually an AND followed by an inverter here. And how about all zeros? It's the same as all ones, but invert the inputs. Okay, see these bubbles? It's the same circuit. Okay, now this circuit, which is in a binary fashion, assumes that all inputs arrive at the same time. What happens if the inputs do not arrive at the same time? In other words, you have early inputs and you have late inputs. Then you implement your circuit in this serial fashion. In other words, you process the signals that come early, and you push the late signals to later gates, right? And this is exactly like, say, for instance, you are filling a bus, and you would like to, as quickly as possible, to take off or drive this bus as quickly as it fills up. So what you do is that when passenger comes, those early passengers, you send them back in the back to the back of the bus, while the late passengers, they sit next to the driver because they come in, they sit quickly. Okay, so this is exactly what happens, is that the signals that come early, we have all the time to process them and go through these gates, but the late signals, you push them to a later state. So when you have the arrival times different, you sort out the early signals, the signals that come early at the bottom, and you put out the late signal at the top, and you kind of implement the AND gate in a serial fashion. Okay, all right. Okay, one thing we do quite often is comparators, and we want to design circuits that compare numbers for us because they have a common usage in VLSI systems. And comparators basically check on the equality of two numbers. or the relationship, whether one is larger than the other one. To do the comparisons, typically what some of the VLSI systems do, they perform a subtraction and they check on the flags to determine the relationship, as we will see shortly. Okay, if we subtract b minus a or a minus b minus a, you check on the carry, and the carry flag indicates if you have a carry, okay, that means that for b minus a, that means that a is greater than or equal a. If there is no carry, b is less than or less than a. And this is basically because the carry typically indicates whenever you have a carry in your operation. Let me just check on one thing here quick. Okay, yeah. Okay, so basically, when we do the subtraction for b minus a, okay, so implementing the minus a is in 2's complement, and the 2's complement basically is by flipping the bits and add and or subtracting, I should say, the a from 2 to the n. And if you have a carry, it means your result really is greater than 2 to the n. Okay, if you do the cancellation appropriately, you will deduce that b is greater than or equal a. If you don't have a carry, it means your final result of the subtraction is less than 2 to the n, because you don't have a carry. And therefore, if you do the cancellation, you will see that b is less than a. So the carry flag indicates for me a meaning about the relationship between these two guys. Okay, in typically, if you want just to check if two numbers are equal, what you do, you send them to XNOR gate, and then you AND. So basically what we do is, to suppose that we want to check if 1 0 1 0, this is a number, and b number 1 0 1 0. Okay, so the XNOR of those is 1, the XNOR of those is 1, the XNOR of those is 1, the XNOR of those is 1. Okay, now I send those numbers into what? Into a 1 detect, which is this one here, and that comes a 1, which means the two numbers are equal. But suppose, for instance, one of these numbers is not, let's say this is a 1 here, for example, then this becomes a 0. Then the output of the AND gate will be a 0. Okay, all right. So this is how this equality, it's a simple circuit, but many times we need more than just equality. We really need to find a relationship for circuits. Okay, so in this case, we study this table, and for unsigned number, when we subtract b minus a, okay, b minus a, and we get flags for this operation, we can use two flags, which is the carry flag and the zero flag. Okay, now if the carry flag is 0, and the zero flag is 0, it means a is greater than b, as we saw earlier. If the carry flag is 1 and the zero flag is 0, then a is less than b. Now, if the carry flag and the zero flag both are 1s, it means a equals 0. The case where the carry flag is 0 and the zero flag is 1 never exists. Okay, so that's the case here. So now, okay, now we can use this never exists case to be a don't care. So if I want now the equality of a and b, I can say, well, if I get a 0 flag, then it means a equals b. Okay, and now if I want a greater than b, which is this one here, for example, a greater than b, I can take these two boxes and I say whenever the carry flag is 0, okay, then a greater than b. And you can go through these cases by using this don't care condition to minimize, but some of them will not be simplified, like this case here. Okay, when a less than b, so it has to be when the carry flag is 1 and when the zero flag is 0. Okay, we'll use this table and we come to the circuit here and say, okay, let's try to do b minus a, and we implement b minus a as follows. This is an adder. This is a carry propagate adder right here. Okay, the carry propagate adder. What I will need to understand how to implement the 2's complement of the a. The 2's complement of the A, as we know, is by inverting the bits of the A plus adding a 1. So this is a carry n equals 1. Okay. Now, then I add B. So there, this adder, what this adder does, it adds B plus the inversion of bits of A plus a 1. So this means what? This is a minus A. So that's how I get B minus A. Now, from this operation, what I will get a carry. I will check the carry flag, and I will check the zero flag. So, well, how do I implement the zero flag? Well, I take the result of the adder and I do a zero detect. I know how to do a zero detect now. A zero detect. Okay, a zero detect circuit. Now, from the zero flag plus the carry flag, I come to the table here and I can implement whatever condition I want. Let's suppose, for example, I want to check if A equals B, which means I need to check on the zero flag. So I take the zero flag, and that means if the zero flag is 1, A equals 1. If the zero flag is 0, A is not equal to B. Right. Okay, now, what happens if I let's say, for example, I need to check on A less than B. A less than B, the A less than or equal B, this is the carry flag. So you can see this carry flag gives me this information. What happens if I want A greater than or equal B? It is the inversion of the carry flag, right? And zero flag. So the inversion of the carry flag and the zero flag gives me, and so I can detect all sort of kind of flags from this circuit. Okay, I can check A less than B, A greater than B, A not equal B, and basically using the concept of adding or subtracting B minus A and understanding the relationship between flags and equalities and relation, I can deduce the relationship from the flags. Okay, so understand one thing, all of this what we have done is for unsigned numbers. For signed numbers, things is a little bit more complicated, and we will not cover this in the class because we need the carry, the zero, the negative, the overflow flag, and the sign flag, and it gets a little messy here, so we'll leave it for a higher grade class. And we are going to stop at counters, and we will finish it off next class. And thank you very much.